Yeah. Cool. Okay, yeah, so I'm Fabian. I work at CoreOS, where I do Prometheus stuff and some Kubernetes-related things. And I want to talk about alerting with time series today. So in general, this is all like high-level stuff. It's not tied to Prometheus, but of course, that's the kind of things we implemented in Prometheus. So first, we want to look at what a time series is. And essentially, it's just a stream of timestamp value pairs associated with some sort of identifier. In the Prometheus case, this looks like this here. We have a metric called HTTP request total, and then there are some dimensions associated with it. So you can basically have multiple series for a single metric that give you insight into certain dimensions. And then you just have a bunch of samples, right? So we have 3 values here, and each has a unique timestamp. And then this can in total look like this. We have a metric, and then we have, for example, a request pass, a status code, and each unique combinations of labels and their values is a new time series. And then you can do cool stuff with them, right? If you have a query language, you can do aggregations and other calculations. So here we have a rate function, which takes a window of 5 minutes over all the series associated with the metric name HTTP request total, and the job equals nginx. And then we get a request rate, and then we can aggregate these again by certain labels. In this case here, request pass and the status code. And what we get is pairs of pass and status, and the rate value for each. And we can evaluate the same stuff over a range of time, and then we get essentially new series. And quickly an overview of how Prometheus collects time series data. Prometheus talks to services coming systems. You can hook up anything you want, basically. We have native integrations for Kubernetes, AWS, Consul, etc., but you can also plug in your custom ones. And by that, Prometheus always knows the state of the world, right? Your service discovery system is a source of truth, and Prometheus just always stays in sync. And so it knows where services or applications to be monitored are running, and can go out and just scrape these for metrics, which are exposed in an open format. And then it stores all these time series data. And then you have an API where you can hook up Grafana or any custom application. And you can also evaluate alerting rules, as we will see later, on the collected data. And the benefit of having time series data as your foundation for alerting is basically that it solves a lot of problems you would have to resolve in your alerting system once again. So for example, you have a lot of traffic to monitor. Let's say you have some sort of web service, and now you're getting scraped or DDoS, or however you want to call it. So some external source is basically increasing your traffic, and this should not cause your monitoring traffic to increase. In an event-based system, this is the case, right? So basically, people are DDoSing you, and you're now DDoSing yourself again by just generating more monitoring traffic. And this doesn't happen in the Prometheus case because we are collecting events already time aggregated from the client. And so the same translates to alerting. If we alert based on time series data, we don't even are affected at all by any external traffic. And then we have a lot of stuff to monitor, at least potentially, right? If you have large infrastructure with microservices and you're running hundreds or thousands of service instances, you just have a lot of stuff you have to basically track. And the service discovery system is helpful here because it already tells you what is where, and your monitoring system just goes out and scrapes the stuff, and you just have one pool of time series data, and the alerting system doesn't even have to know where it's coming from. And this also helps with constant change that's happening in infrastructure, right? If you're scaling deployments up or down, or do rolling releases, new instances appear. And if your time series system already covers this, your alerting system doesn't have to even know about this change. And then you want, in general, a fleet-wide overview, and that's where a data model of time series with dimensions helps you, because you have a query language that allows you to calculate aggregations and get this high-level overview of very complex and rich raw data. But as we store this raw data, we're still able to drill down, right? We never lose any detail because all the aggregations happen at query time. So all these benefits of time series sort of directly translate into alerting if we build our alerting on top of this time series data. Oh, different point. And also you want to monitor ideally all levels with the same system, right? You want to monitor your switches, your routers, your nodes, your applications running on them, everything with one system, because it makes it easier to correlate data about different things. And you don't have to basically teach all your engineers and teams different systems to use. And this also then of course, directly translates into your alerting. And how can we make sense of all this time series data? It's potentially billions and billions of samples every day about all aspects of your infrastructure, and now we somehow have to turn this into something that allows you to have meaningful alerting. And the go-to answer often is do some anomaly detection, right? You have sort of big data, so do big data stuff with it. The problem with that is that if you're actually monitoring at scale and collecting really, really rich data, something is always correlating. So some smart machine learning algorithm might be able to detect problems in 1,000 different time series, but if you have 20, 30, 40, 50 million time series, there's always some noise that is probably triggering some signal. And then you get paged a lot, and that's just not healthy, right? If 99% of your pages are actually not something that's meaningful, people stop paying attention and stop actually reacting to pages. So you can't have that. Then you have to tweak your methods so we have less false positive. At some point this will mean that you will have false negatives, and that's something you cannot tolerate again. Like a single false negative potentially means that your entire infrastructure is down and nobody's being notified. So in Prometheus, or in general with time series-based alerting, we try to solve this differently. We try to be very explicit about what is the desired condition and in which condition are we not happy anymore. And it's quite simple actually, because you have a current state which is captured by time series, and you should be able to very explicitly define what's my desired state. How should things be like? And the delta of that is what you want to alert on. That's basically it. And time series-based alerting is basically about finding this delta. And essentially, that's something Brian talked about this morning already. You want to have symptom-based pages. So anything that actually wakes someone up should be something that's an urgent issue affecting your user, and it's also actionable. And this means if you have a system that you want to define alerting for, you look at the boundary between the system user and the system itself. So user can be an end user, like a customer, but it can also be an internal service that's basically requesting your service, or a database, etc. And of course, any system often has dependencies as well. But these actually don't matter, because the only thing we care about is if our user is having a good experience. And if our dependency is affected, this might or might not mean that my user is affected. And there are actually 4 basic signals that you can use to define alerting with. And one of them is latency. So if you're providing a service, there's also always some sort of time bound, right? You want to provide the service in a reasonable amount of time. Users don't want to wait for 10 minutes until they see your website. So you probably want it to be at the order of 10 milliseconds to, I don't know, 2 seconds. That's basically something really simple, right? You can define an alert on latency. And if this is violated, then your user is having a bad experience and you can page someone. There's also traffic. So if you have a service, you expect the service to have traffic, and if the traffic drops to 0, something's probably wrong. And closely related, there are errors. So if you provide a service, you don't want all requests to error, or like too many requests to error, but there's always some sort of percentage, right? So you probably have a tolerance threshold of 0.5% of your requests being allowed to error. And if it goes above that, you also want to alert. And then there are cause-based warnings, and they are a bit different. So you can alert on a lot of other stuff as well. You can alert on system internals, for example, garbage collection being too slow. You can alert on dependencies of your service being down or not reachable or slow. But all these don't necessarily matter. So if you design a resilient system, it might actually be made to deal with dependencies being slow. And the user's not affected. So the operator of the system does not have to be paged. So in general, everything that's not the boundary between the system and the user is helpful to investigate an actual issue, but you don't want to page on this stuff. There's one exception, basically, and that's the false golden signal, saturation or capacity. So, for example, disk space running out, file descriptors running out, memory running out, all this kind of stuff. That's stuff where you can actually sort of predict where it's going, and if your disk space is going to be full in 1 hour, you're going to have a really big problem in 1 hour. So that's probably something you want to detect early before there's an actual symptom, and fix beforehand. So now by example, how can we do this time series-based alerting? And we just take Prometheus because it's kind of what we do, and it's kind of easy to understand. You define alerts on the machine collecting the data. So the Prometheus instance collecting data is also the one that's evaluating whether the data indicates an alert. And we have a simple DSL for that. So you specify an alert by the alert keyword, and then you provide a name, and then you provide any Prometheus query language expression. And that's the same query language you use for graphing. So you can directly take a graphing query and put it into an alerting rule, and it will be fully working alert. And then you can define a for condition, which is kind of a time period that avoids flapping alerts. So you say if this alert triggers for 5 minutes, then actually send something out, because it might just be a short blip, which sort of heals itself, and then you don't have to page someone. And labels and annotations are just context information you can attach to alerts being sent out. We will see this later, but it's not too important for now. And what you will get out from an alerting query is the same that you will get from a regular Prometheus query. You essentially get back a vector of elements, where each element is a label set, and then you have one value associated with it. So for example, we have a metric called etcd has leader, which is 1 if an etcd instance has a leader, and 0 if not. And we split this out by the instance name, ABC in this case, and job, which just indicates the service. So here we have obviously instance A and B without the leader, and C can see a leader. And now we want to alert on instances that don't have a leader. That's super straightforward. We just say etcd has leader equals 0. And if that condition is true for 1 minute, then you send out an alert. And you attach the label 0 video page, which is later used downstream in your routing system to define how to notify about a certain alert. Yeah, and the alert in the end is also just a label set, as we can see here. So now 2 more complex examples. We have a metric request total, and that's just a counter which is incremented for every request the application receives. And it's split out by the request path, by the instance obviously, and by the request method. And in the same way we have a counter for errors for these requests, which is split out by the same path. So in the end, request errors divided by request total will give you the percentage of errors you currently are seeing. So now we want to define an alert, and first of all we have to take a rate, because this is just a counter, and we want to get the per second value over a certain time window. In this case here, 5 minutes. And then we have, for every single series, we have now a request error per second rate. And we want to sum this up, right? Because if we have 200 service instances, this would otherwise yield up to 200 alerts. So we sum this up and say, if this is greater than 500, so more than 500 errors a second, we want to alert. And the problem here is that this is an absolute threshold. So this alerting rule needs constant tuning whenever your scale changes, which can mean different things. So either over a day your traffic changes, right? You have sort of a curve of your users being active or not. So over time, the threshold here in the dashed line changes its semantic meaning with respect to the total traffic you have. So this is not really good, because at the spikes throughout the day, it will trigger even though nothing really changed. Another case is traffic over months, right? You are have a growing user base, and people are just using the service more, and now you always have to go and check, did my total traffic increase, and should I adjust this alert again and again. And similarly, just spikes, for example, if you get I don't know, popular on Twitter or something, and a lot of people are coming into your site, this also causes spikes, and this also might cause your error rate to go above the threshold, even though it just stayed the same with respect to the total traffic. So to avoid this, we can just obviously take the errors relative to the total traffic. So we now divide what we did before by the total request rate. And now can say if the fraction is greater than 1%, then we want to be alerted. Which means we now defined for our entire service, for all the instances, a global threshold of 1% of requests that are allowed to error before we page someone. And that's better, because now the dashed line is sort of adaptive to our traffic. That's pretty nice. But the problem here is that we are losing dimensionality. So we are losing detail, and signals might cancel out. The simplest case is, let's say you have a contact form, which is probably rarely used with respect to your index page, right? And now your contact form can actually error every single time a user requests it, but it will totally be lost in the noise of the index being the index page always loading successfully. So the sum can be this blue line here, right? Which is like way below the threshold, but a certain path or request method can actually be erroring way too often. So we want to preserve this detail. And for that we can actually preserve certain label dimensions of our metrics in the aggregations we do. So now we don't sum everything. We have each, and now we can them to implement kind of threshold. And now we can, in our letting, see for every single pass whether it's above the threshold or not. That's still wrong, obviously, and intentionally, because we have to take care of which dimensions we actually use here. If you have a microservice architecture, you're sort of scaling horizontally for fault tolerance and scalability and all. And a single instance failing is actually something you are totally willing to deal with, right? I mean, that's why you did this whole thing. So you might have one instance out of 1,000 that's acting up and erroring a lot, but that's totally fine, right? It's like, it's not going to impact your entire service you provide too much. So you probably don't want to include this in your alerting because your system is supposed to deal with this failure and not some operations engineer. So we can actually invert this aggregation condition and not say which labels we want to preserve, but which labels we want to aggregate away. And that's way more powerful because it's easy to, by accident, drop a dimension if you sum by something, but you have to be very, very explicit about which dimensions you want to drop. And you can just put in your aggregation the dimensions you are fault tolerant along, in this case here, the service instance, and it will preserve everything else. And what we now get is pairs of method and pass, and for each of these we now apply this threshold. And that's in the end what we wanted in the first place. For our entire service, we now have one rule that gives us a full latency detection on any bad conditions. So one alert covering an entire service, or potentially even multiple services if they all have the same metrics. Yeah, that was the example for latency. Another thing is error rates. That was error rates, sorry. Latencies work similarly. You also can just calculate latencies for all your service instances and split this out by certain dimensions and apply dynamic thresholds. Another rather different thing is course-based warnings. So running out of disk space, running out of file descriptors, running out of memory. You want to detect these early. And what usually systems do is they probe your hard drive, check how much space is left, 80% for example, and if it's above a certain threshold, they will tell you that this is a bad condition. There are several problems here. You usually set this to like 80%, because if you set it to 90, and the disk is filling up really fast, you won't have time to react. That's why you set it way below what you actually could be using of your disk. Another case is, say your disk is 10% full, and it's filling up really, really fast. Now your alert won't hit until you hit like 80%, and then you have no time to react because it will take another 3 minutes until your drive is actually full. So just probably the current state doesn't really get you anywhere, at least not reliably. What you actually want is you want to look at a range of time and see how this resource is developing. So is this disk full but staying basically constant, or is it filling up really fast? And we can do this, right? We can look at our time series data, which we collected over time. Look at where's the disk, how much free disk space we have now, and how much we had 1 hour ago. And based on that development, make a prediction, where will it be in 4 hours? And if this gives you that it will be completely full, then you can alert someone early without having any absolute threshold. And what Prometheus does here in this case with linear prediction is it does linear regression on the interval of 1 hour we specify, and then tries to estimate where we will end up. And this actually is one alert which covers every single hard drive in your entire infrastructure. And you can apply similar alerting for file descriptors, memory usage, etc. We also can see a nice use of annotations here. So we want to provide the receiver of the alert with some detail, right? Just sending a disk full within 4 hours is not really helpful if you don't know which drive is actually affected. And of course, this information is preserved in the label dimensions. And we can use these label dimensions that are in every alert to define annotations which give you rich information about what's going on. So here, for example, is a description. And for every alert that's generated, we generate one description which is templated using labels here. And can specify, the alert you will get will specify very clearly which device is affected, on which mount point, and on which machine. So this was the Prometheus side. These rules are put on your Prometheus machine or any other time series-based system and are constantly evaluated. And as soon as some of these yield any results, there's an alert and we want to push it out somewhere. And in a general case, you could just push them directly to the user by sending an email, contacting PagerDuty or anything else. But that's not really meaningful or helpful. Because A, you want to have redundancy, you want to have multiple machines evaluating the same alerts, and you don't want to get duplicates. Also, you want to aggregate alerts. Just because alerts are not super noisy, they can still be quite a lot about a single service. And ideally, you just want to get a single page telling you that something is wrong, and then you have the rest of the time to react and won't spend it acknowledging pages about the same thing. And also, you want to do some sort of advanced routing, and you don't want this to live directly in your monitoring system. And that's why we have the alert manager. And that sort of sits outside of Prometheus. And it's an HA component, which runs on multiple nodes at once, and it's communicating. And you send out all the alerts to the alert manager, which then cares about deduplication, aggregation, and routing. And then dispatches notifications about one or more alerts to different integrations like different chats, PagerDuty, email, Opsgenie, etc. So to visualize this a bit, let's say we have alerting rules sitting in some Prometheus machines. Doesn't really matter which one, but they're generating alerts. And a single alerting rule can potentially generate thousands of alerts every second, in theory at least. And what you get is this stream of stuff. High latency for service X, in zone EU West, for this pass, for this method. And then the next one is about a different pass. And then the next one is a duplication of that one. Just this stream falling out. And that's not really what you want to receive, right? You don't want to get all these pages every few seconds. So the alert manager lays in between this and receives all this stuff and tries to group it. So if you have a certain service and have several alerts defined acting on the service, the alert manager knows how to now take all these alerts belonging to the same service and putting them into one notification. And what you then get is something like an email or a page telling you you have 15 alerts for this certain service in this certain data center. 3 of them are about latency, 10 of them are about high error rate, and 2 of them are about some caching server being slow. And then you get a detail of all these alerts. But you get one page telling you basically about one problem that belongs together. And you won't basically spend all this time acknowledging. And also it knows how to do inhibition, and that's sort of an advanced feature. But let's say you have an alert that tells you that your data center is burning down. That will probably affect quite a few things in this data center, and they will probably all generate alerts and pages. But now you are waking up 20 to 30 people for a problem they can't really deal with, right? There's one person that knows how to deal with the data center being on fire, and nobody else really needs to do anything at this point. And that's just like one extreme example of inhibition, but that's also a feature of the alert manager. And of course, it can handle silencing for you. So basically, you get these alerts, which are sets of labels, and you can silence for certain periods of time along certain labels. So if you're taking a service into maintenance, you can just silence all the alerts and have the label service equals X. So anomaly detection. People still want this in a way for certain things. It's really not necessary. If you just cover these 4 golden signals, you have really reliable alerting, but you can do it. And as I said before, there's really no magic thing that detects from all your data all possible problems, but you can do something practical, right? You can specify the problem domain, which normally do want to detect, about which metrics, and then you can define some sort of like unprecise soft estimations of things that might be wrong, but which might not necessarily indicate a serious problem. And these can be helpful and interesting, but they should probably never be paging. So as one example, we have requests, which are the blue line here, and they're kind of spiky, but we want to alert now on requests over courses of days being out of the normal. So for example, if you want to alert if your requests you're getting currently are 20% lower than they were last week at the same time. And in Prometheus you can actually do that. So we can calculate the request rate first on our request total metric and calculate this for the entire service. And now we can apply hold winters, which is an exponential smoothing function, which gives us this red curve here. So out of this like spiky curve, we get this smooth curve, giving us some sort of accurate representation of traffic development over courses of days. And now we can use these metrics we just generated to calculate this alert that notifies us if our traffic is 20% up or down, out of the 20% range of the traffic last week. So, yeah, we take our current request rate, and then we take the smoothened curve we calculated from 7 days ago. And if the current request rate is out of the 20% range of this, we want to alert. So this theoretically is anomaly detection depending on how you define it. Another example stolen from Brian here. This is sort of just to show, even if you specify very clearly what the condition is you want to alert on and what you consider abnormal, even then it's really, really hard to get right. And this is a sort of like stress how hard it is to actually automate completely. So let's say we have the latency in seconds for a certain service instance over the last 5 minutes. And we want to alert if any particular instance has a latency that's out of the 2 standard deviation range of the average of all the other instances. So basically, one instance has a high latency with respect to all the other ones. And that's sort of the expression that you could use in Prometheus. That's pretty advanced, powerful, etc. But now we realize that most of your instances have a latency that's almost exactly the same. So they are very tightly clustered. And now even a small deviation of one single instance actually would trigger this, because the standard deviation is really low. So you can add another condition to basically catch this one edge case. And you put it into the same expression, and now you just specify that the latency of this abnormal instance also has to be 20% in total higher than all the other ones. So we combine basically the standard deviation with with the relative. Yeah. Okay, and then we realized that actually service instances that are not requested often are sort of cold. They have cold caches. They take very long. So you only want to apply this to instances that are actually receiving more than 1 request per second. And now you have a relatively complex expression, just basically to catch some edge cases that you encountered, right? And imagining this being completely automated by any sort of machine learning system, you can kind of guess how well this is going to go. Self-healing, also possible if you want. So in theory, Prometheus scrapes something, gets metrics, evaluates an alert, sends out a notification about this alert, and the alert manager can actually hook up and notify any system you want. So you can just write your own webhook that the alert manager sends alerts to, that then evaluates these alerts, expands the label sets, checks what the alert is about, and can then take action. So in theory, let's say you have an NTP drift, and you just want an automated system that just sort of restarts a node whenever this happens, and you can define an alert on that. Alert manager notifies this just sort of small server that just reboots nodes, and this one can take actions based on the alerts that came in. So much for self-healing. That can also be built in theory if you want to. So in conclusion, you want symptom-based pages. Everything you wake someone about should be from the boundary of the service and the user of the service, and should be actionable. Anything cost-based from internals of your service or dependencies of it is helpful during the investigation, but it should just be a warning flashing somewhere that does not interrupt someone's work or sleep. And your alerts should always be adaptive to change. They should preserve as many dimensions as they can, but be very sure to aggregate array dimensions that you're fault tolerant along and that you want to ignore. And for anything related to capacity planning or saturation detection, you want to use linear prediction. Yeah, and if you want to, you can do anomaly detection. Their alerting expressions are very powerful. You can go as far as you want, but you probably don't need it, and you certainly should have a page on it. And the raw alerts generated by these alerting rules should not be consumed directly by a human. There should always be some sort of intermediate layer, like the alert manager, that actually does aggregation and meaningful routing of alerts. And that's it.
So are there any questions for Fabian? Put your hand up. There's number one I saw.
Cool.
So I have two quick questions. First is around the alert manager. Can you submit alerts into it from other systems other than Prometheus? Or is it better to go into Prometheus and into the alert manager?
It has an API, so you can in theory. There are some semantical considerations you have to take. It's documented. You can't just send anything, you have to adhere to some rules, but it's possible, yeah.
Okay. And then the second question is around inhibition, the alert inhibition. Can you do that at runtime, or is that something, I mean, so if I see a load of things...
Stop talking or leave, thank you.
So yeah, inhibition, can you send a message to, again, the alert manager to say there's a short-term inhibition until another state happens, or...?
They are not time-based, they are purely label-based and are configured, but you can theoretically just change the configuration file and reload it.
It sounds like you're looking for a silence,
Yeah.
which can temporarily suppress given an alert. Second question is down here.
We want to monitor how many nodes in the cluster are offline, for example. In this case, should be done using the description of an alert, or in alert manager should aggregate and decide where to notify a human if like 20% of nodes in the cluster are offline.
So the question is, who is responsible of actually notifying humans?
Then which module, the alert manager or the alert itself, should include a rule that certain number of nodes are offline, the aggregation threshold.
So the question is where to do the aggregation in the alerting rule versus in the alert manager. That always depends a bit, right? Ideally, you want to aggregate the least amount you can in the loading rules, which is like the dimensions of fault tolerance, like the instance in a microservice. Yeah, you should do the least amount of aggregation in the loading rule, but as much as necessary, basically.
Why are you all congregating the questions in one section?
Hi. Some of the rules that you're using to, those queries you're using to define alerts looked pretty sophisticated. Do you have a way of testing those without actually having to deploy them to real systems so that you know that...
So we have to come up there. It's squeaky.
The question is, do we have unit tests for rules?
The question was, do we have unit tests for rules? No, but we want to. That's basically it.
Now you're on that side of the room.
Okay, I missed a bit of the talk, so I hope you didn't cover it already, but sometimes the exporters of data for Prometheus, when the application fails, but the exporter is still running, they just do not export new metrics. So how would be a good way to have an alert that triggers when no new metric appears on that metric? Well, no new values for that metric.
Yes, so in general, so the question is, if we have an exporter that exports metric or an application, and the application is down, but the exporter is still alive and exporting metrics, how do we alert on the application being down? And the general case is just you have the exporter having a metric where that can reach the application itself. And then you alert on this single time series or metric.
Any other questions? Someone on this side, please. Don't have to run around again. Any more questions? Going once? Going twice? On? Thank you, Fabian. So the next talk is in 7 minutes, isn't it? Or 25 past. And there's still stickers here for Prometheus, and if you are talking about Prometheus conference, you can grab a stack.